All right, hi everyone, welcome back. And now let's talk about the duality theory, right? So, all right, so remember, let's consider a linear program and the linear program in standard form, right? So we're minimizing a linear function like C transpose X, subject to AX equals to B, and X is non-negative. All right, so from Farkas lemma, what we saw is that, okay, so we saw that AX equals to B and X greater or equal to 0 has a solution, so it's feasible, right? So this will address the first question, like it's feasible if and only if, right, Y transpose B is greater or equal to 0 for each Y in Rm, such that Y transpose A is greater or equal to 0, right? And all right, but now if we look at what happens to the linear program, just when we multiply Y transpose A, right? So we just multiply the equality by Y transpose, here's what happens, right? So if, okay, so if we had, suppose that we had this equation, okay? So Y transpose A is a row vector, right? So if this is less than or equal to C transpose, and by less than or equal, I mean that it's less than or equal in coordinate wise, right? So then what do we have? Well, we have that Y transpose AX will be less than or equal than C transpose X. And this first implication is because X is non-negative, right? So X is non-negative. But now here's the thing. We're using the standard form. And we have that AX is actually equals to B, correct? So if we found any vector Y such that Y transpose A is less than or equal to C transpose, okay, so if this happens, then we know that Y transpose B is less than or equal than C transpose X, right? But what does this say? Well, but if you remember, like C transpose X is our objective function, right? So C transpose X, this is exactly our objective function. So if we find any vector Y such that Y transpose A is less than or equal than C transpose, then we have that Y transpose B is a lower bound on the solution to our linear program. Does that make sense? Because, and this inequality, note that this inequality that we just proved here holds for any solution to our linear program. And therefore, if it works for any solution, it works for the minimum. And that's why we have that any solution Y of this other linear program is a lower bound on the solution to our current linear program. Does that make sense? So this motivates us to define another linear program, which is called the dual of the linear program that we're studying in the beginning, right? So we started with the linear program on the left, and then somehow we obtained the linear program on the right. Because the first thing that we did is, well, suppose that we had these constraints. Then we noticed that any Y satisfying the constraint above, right? Like the constraint in the box here, right? So any Y satisfying this constraint is a lower bound. So then this dual linear program, what are we doing? Well, what we're doing is we are here maximizing, right? Well, any Y satisfying the constraint, right? Sorry, let me say here, implies that Y transpose B is a lower bound on the primal. So we might as well create a linear program. And what are we doing? We're maximizing the lower bound, right? So the dual linear program here, LP, is maximizing lower bound to the primal via the constraint, right? Like via the constraint y transpose A less than or equal than C transpose. Does that make sense? So then what we have here is that to each linear program that we have, there is a dual linear program that we can obtain, where the dual linear program, okay, the optimum of the dual linear program is the lower bound on the optimum of the primal, and vice versa, right? So, okay, great. All right. And so from the previous slide, what did we show, right? So we just showed that, you know, y transpose A less than or equal than C transpose, y transpose B is a lower bound. And so the optimum, like the maximum value of the dual, lower bounds the optimum, the minimum value of the primal, right? And this is what's known, okay? So this is already what is known as weak duality. Of linear program. Okay, so we just proved already the weak duality for linear programming. And okay, and what does the weak duality says, right? Is that if X is a feasible solution of the primal and Y is a feasible solution of the dual, then we must have that Y transpose B is less than or equal than C transpose X. Okay, and why is this important? Well, this is important because the thing is, now to certify that your linear program, like that you have a pretty good solution, all you need to do is to get a feasible solution of another linear program. So suppose that we knew how to find feasible solutions, okay, just for now. So if I know how to find feasible solutions of the linear program, then I also know a lower bound on the optimum of my primal linear program. Does that make sense? And the lower bound is just say, okay, pick any feasible solution of the dual. That's a lower bound. We know we cannot go lower than that, right? So then ideally, if you can get this gap really, really close, right, we would hope to say, well, okay, if I could be able to keep decreasing this gap, I'll be able to get to my optimal solution, right? And this is actually the basis of some algorithms which are called primal dual algorithms, okay? So this is the motivation for those algorithms, okay? But now what I want to talk about is some remarks on duality and actually to notice that some stronger things actually hold, right? All right, but before we go on, let's just make some remarks, right? So we just noticed that the optimum, the maximum value of the dual lower bounds the minimum value of the primal, right? So we know the solutions to the left, they are less than or equal than the solutions to the right, right? If we talk about solutions. Okay, now suppose that alpha star and beta star, they are optimal primes for the optimal values for the primal and dual. What do I mean by optimal value of a program? The optimal value is exactly the value that minimizes. So alpha star is the minimum here and beta star is the maximum here. Okay, so all right, now what we showed is that when both primal and dual are feasible, we showed what? We showed that the maximum of the dual, which is beta star, is less than or equal than alpha star, which is the minimum of the primal, right? Now you may be wondering, well, is equality actually hold, right? And that's the content of the strong duality for linear programming, which we're going to discuss next, right? So, but before then, we should just say, if the primal is unbounded, okay, so let's say if alpha is equal to minus infinity, then it means that the dual is infeasible, right? Because this beta star is infeasible if and only if there's actually no solution to the dual. Because if there was one solution, we know that the maximum cannot be minus infinity. Does that make sense? Okay. So then now, if the dual is unbounded, and here unbounded because it's a maximization problem. So if beta star is equal to infinity, then the primal is infeasible, right? Because alpha star is infinity. But now notice that if the primal were feasible, then the minimum is upper bounded by any feasible solution, right? So, okay. And here's a practice problem, right? So you would also wanted to see is that the dual of the dual linear program is actually the primal. And that's why we call this duality. There's no chain. It's just, if I take the duality, I get my dual. And if I take the dual of the dual, I get the primal again. Okay. So, and to do that, you can just convert the dual into standard form and then take the dual version. And once you convert it back to standard form, you get exactly the primal. Okay. So, okay, so this is a practice problem for you. And now the question is, okay, when is the above inequality tight? Right? So that's the kind of pressing question that we have once we see linear program duality, right? The weak duality theorem. And okay, so what strong duality tells us is that if alpha star and beta star are the optimal values of the primal dual, then strong duality says that if the primal and the dual are feasible, okay, if they're not empty sets, right, then the max of the dual, which is beta star, is equal to the minimum of the primal, which means that both programs have the same value. Does that make sense? i.e., both programs have the same value. Okay, and as we can, as we'll see, this has really impressive applications in learning theory and combinatorics, and it also has important applications in game theory. Okay, so this is going to be the content of the next lecture. All right, so how do we prove this theorem, right? The strong duality theorem. Okay, so here's how we prove. So since we already proved weak duality, right, it suffices to show the following. Okay, so let's come up with a linear program that just tells me that, okay, the max of the dual is equal to the minimum of the primal if and only if a certain linear program has a feasible solution. Does that make sense? So, and the idea is to come up with this linear program. We're going to maximize 0. And when we say maximize 0, just because we don't care what we're maximizing, right? So this is equivalent to saying that we don't care about what we're maximizing. And when we don't care about what we're maximizing, this is usually what is called like a feasibility linear program, right? We just want to check if the linear program is feasible or not. Now, let's look at these constraints that I put here. If you remember the primal, so what did the primal say? So the primal was saying what? We want to minimize C transpose X subject to AX equals to B and X greater or equal to 0. And the dual was maximize Y transpose B subject to Y transpose A less than or equal to C transpose, correct? So now let's look at what this linear program that we came up with is capturing. Well, first of all, this inequality comes from the dual, correct? This equality, these inequalities come from the primal, right? So all this is saying is that if it has a solution, then Y is the solution of the dual, right? So Y is a solution to the dual problem. X is solution to the primal. But there's this extra little inequality here, right? And what is this inequality? Well, let's unpack. If we rewrite this inequality, we say C transpose X less than or equal than Y transpose B. But if you pay attention, you're like, well, Rafael, wasn't weak duality actually giving us the other inequality, right? And the answer is yes, right? So we know that weak duality shows that if X and Y are feasible, like they're feasible primal dual, then we know that Y transpose B is less than or equal to C transpose X. But now, well, if the values of the programs, they're the same, right? It better have a solution, X and Y, a pair, such that Y transpose B is equal to the value of C transpose X. Does that make sense? Because this will happen if and only if, right, the max of the dual is equal to the minimum of the primal. So then we're just trying to say, well, this is the opposite inequality. Because now we're trying to say, if we have, like, for any solution that is, if X is a solution to the primal and Y is a solution to the dual, we already know that Y transpose B is less than or equal than C transpose X. We already know that. So now all we need to know is to certify that this would imply is equivalent to saying that X and Y are optimum solutions. Does that make sense? So I can pause here, and then if it doesn't make sense, you can ask in the chat or not. Okay, so now all we did is we picked the statement that we wanted to prove, and we encoded the statement itself in a linear program, right? In a feasible linear program. And now, since we have this linear program, let's just apply one of the variants of Farkas lemma that we learned, right? And which variant are we going to apply? Let's apply variant 2 of Farkas lemma, because now notice that we have just a bunch of inequalities as well. We don't have like equality, right? So we can apply variant 2, okay? And we're going to recall the variant 2 here. So now, if we look at the linear program from the previous page, which I can just like slide here. If you look at this linear program from the previous page, it can be encoded by some matrix B, and the matrix B is exactly this matrix here. And B times XY is less than or equal than these equations. Now let's unpack what these equations are doing, right? Well, the first inequality is just saying that AX is less than or equal to B. The second inequality is saying minus AX is less than or equal than minus B, but this is equivalent to saying that AX is greater or equal to B. So those two together are encoding AX equals to B, right? Now, the third inequality is just saying C transpose X minus B transpose Y is less than or equal to 0, which is equivalent to C transpose X less than or equal than Y transpose B, right? So those are inner product of vectors, so you can always exchange, right? So, okay, so this is good. And the last inequality is just encompassing what? Like A transpose Y less than or equal to C, which is equivalent to Y transpose A less than or equal than C transpose, right? So you can see that all the four inequalities that we had here, so we had one inequality, two inequality, and then this is the fourth. This is the first two inequalities, right, are encompassed as this equality. Okay, so we can encode this linear program as the following linear program, and of course we're requiring the X is non-negative, right? All right, so what does the variant 2 of Farkas lemma tells us? Well, the variant 2 of Farkas lemma, it gives us that this system, okay, has a solution, okay, if and only if, okay, so let me just rewrite the variant here. So the variant would just say that is if and only if there exists a Z such that ZB, if ZB is 0 and Z is greater or equal to 0, right? It implies that Z times this vector here, B minus B 0 C, has to be greater or equal to 0. Okay, that's what variant 2 says, right? So variant 2 variant 2 of Farkas lemma. Okay, but now I'm just unpacking, but you say, okay, why are you writing Z in such a weird way? Well, I'm just breaking up Z into its blocks that multiply properly by B, right? So ZB equals to 0. Then we have, what is this product here? So if I just rewrite this product, I just noticed that if this is like U transpose, V transpose, lambda, and W transpose, if I multiply this by B minus B 0 C, I just get exactly that this is equal to U transpose B minus V transpose B plus W transpose C, because the lambda multiplies by 0, right? So it's 0. And then we need this to be greater or equal to 0. Okay? So that's all. There's nothing magical here. I'm just applying the variant 2 of Farkas lemma. And now, all right, now we have 2 cases to analyze, right? The first case is, suppose that, remember, we have to say that if for all, okay, so remember, the variant 2 of Farkas lemma is that for all, and for all here, I put for each because they mean the same thing, right? For each Z, which is non-negative, and ZB is equal to 0, we have that this inequality holds. So to verify that this system that we came up with satisfies the variant of Farkas lemma, right? Because this is equivalent to proving that the system is feasible. Does that make sense? Farkas lemma says this system above here, the system in red, this system is feasible if and only if the inequality holds for every non-negative Z with that property. Does that make sense? So now we're going to actually use this new linear program to show that this linear program in red is feasible, right? So now let's see. Okay, let's take one feasible solution Z, and the feasible solution Z is a non-negative vector. So there's only 2 cases, right? One case is that lambda is bigger than 0, and the other case is that lambda is equal to 0, right? Like this takes care of all the possible solutions. Now, if lambda is bigger than 0, what do we do? Right? So if lambda is bigger than 0, then we have, all right, so let's see the inequalities that we have, right? So, okay. So let's just multiply like lambda bigger than 0. So, all right, so let's look at our equation here, like Z times B, right? So we know that Z times B is equal to what? U transpose, B transpose, lambda, W transpose. And what is B? B is A minus A. Sorry, that's why I put it up. So C transpose 0. And then we have 0, 0 minus B transpose. Just see, because I always get the signs wrong. A transpose, right? And now we need this to be 0. But what is this, right? So this is equal to 0. But what is this? Well, let's do the multiplication. This is exactly equal to, well, my first row I have U transpose minus V transpose A. So is a 2 vector, right? So this is going to be a 0, 0. So this is U transpose minus V transpose A plus lambda C transpose. And the other one is W transpose A transpose minus lambda B transpose, right? So ZB equals to 0 is equivalent to having what? The 2 equations that lambda C transpose is equal to U transpose minus V transpose A. Sorry, this V minus U here. Let me put the sign already changed, right? And lambda B transpose equals to omega transpose A transpose, or equivalently, we can write lambda B equals to AW. Okay, so far so good. So I'm just writing what it means to have ZB equals to 0. So we have these two equalities, right? All right, so now if we go back, let's see. So this is one of the equalities that we proved. Now, if lambda is bigger than 0, we have that lambda C transpose is equal to V transpose minus U transpose A, which means that when I multiply both sides by W, what do I get? I get lambda C transpose W, which is equal to V transpose minus U transpose AW. But now, if we notice, what do we have here, right? So, okay. So now, okay, one second. Let me put this a little bit further down. So this is just explaining the implication here. And now, if we look at what we want to prove that is non-negative, what do we have? Well, so notice that if lambda is bigger than 0, then we know that U transpose, let me put it here, like lambda bigger than 0 implies that U transpose minus V transpose B plus W transpose C is greater or equal to 0 if and only if, when I multiply by lambda, the same equation inequality holds, right? Like lambda U transpose minus V transpose B plus W transpose C, all of this is also greater or equal to 0, right? Just because an inequality doesn't change if I multiply both sides by a positive number, right? So it's just enough to prove that lambda times that is non-negative. But now, what do we get? Well, now we get, if we multiply everyone by lambda, we get lambda times U transpose minus V transpose B plus lambda W transpose C. But remember, W transpose C is equal to C transpose W because they are just vectors, right? So this is the same number. Now, if we use the inequality above, we just substitute this by the formula that we have. Maybe let me use another color. Just substitute this by this. Does that make sense? And now, what do we get? We are getting here that, so this is equal, and now, but this is equal as well to U transpose minus V transpose. And then we have what? Lambda B minus AW. But if you notice this lambda B minus AW, what is this? Lambda B is exactly equal to AW. Does that make sense? Because we know that ZB is equal to 0. So now, well, this is equal to 0. So this is equal to 0. So if lambda is bigger than 0 in our vector Z, then we know that this inequality holds, because what happens here is exactly that I have that this quantity has to be equal to 0. Okay? So this deals with the case that lambda is bigger than 0. Does that make sense? Any questions so far?
What did we prove at the end? Like what is equal to 0?
Sorry?
At the end, what did we prove that's equal to 0?
Well, we proved that the whole thing, that we are proving that this inequality here is equal to, this expression is equal to 0, right?
And how does that imply the strong duality?
Well, it doesn't yet, right? It implies in this case, because what do we want to prove? We want to prove that for any vector Z that satisfies ZB equal to 0, then this inequality holds, right? And now we just said if Z has its lambda coordinate bigger than 0, then this inequality is actually an equality. Does that make sense?
Okay. Okay. Yeah. Thanks. Yeah.
Good. Okay. Any more questions? This is a great question. So any more questions? Okay. So now we know that if this lambda is bigger than 0, we're good. But now it comes the other case, which is lambda equal to 0. right? And if you notice, well, so far we have not used anything about the linear programs, right? Like, well, we have to use that they're feasible because that's the assumption of the theorem. And now we're going to use the assumption. Okay, so now let's say that X and Y are feasible solutions, which remember, we assume them to exist, right? We assume that both the primal and the dual were feasible. So, okay, so if X is greater or equal to 0, right? So, sorry, X is a feasible solution to the primal program. So we know that X is greater or equal to 0. We know that AX is equal to B. And we also know that Y transpose A is less than or equal to C transpose, right? Just because X and Y are feasible solutions, right? That's what it means for them to be feasible solutions. But now, here's what happens. Well, our lambda is equal to 0. So we cannot use this equality here. We cannot use that equality, right? All right, but what we do know, right, is that, all right, so what do we know? Well, if we take C transpose W, let's just look again at C transpose W, right? Well, here, notice that W is a non-negative vector because it is a coordinate of Z, right? So because W is non-negative, and we know that Y transpose A is less than or equal than C transpose, we can replace C transpose by Y transpose W, and we get this first inequality. Does that make sense? Okay, excellent. But now, what else do we know? Well, okay. Now, so let me go here to the lambda equals to 0, right? So if lambda is equal to 0, okay, what do we have? Okay, if you remember this equality, so if lambda is equal to 0 and like ZB equals to 0 implies what are the two equalities that we have? Well, let's look at the equalities here and let's see what do they become when I replace lambda by 0. Well, first of all, we have that V transpose minus U transpose A has to be equal to 0, and W transpose A transpose is equal to 0, which is equivalent here to AW equals to 0. Does that make sense? This is just because we're in the case of lambda equals to 0. And now what happens? Well, we had, let's look at C transpose W. And as we saw, well, C transpose, like, this is greater or equal than Y transpose A W, right? And this was just because, remember, Y transpose A is less than or equal to C, and W is greater or equal to 0. And then, well, now AW here, AW is equal to 0. So this is equal to 0, correct? But now, what else is equal to 0? Well, A, this is V transpose minus U transpose A, is also equal to 0. Well, but this is a number, right? So, but if I multiply by anything here, I also get 0, right? Because this is a 0 vector, right? So if I have V transpose minus U transpose AX, this is also equal to 0 because this part is equal to 0. Now, what happens? Well, if you notice, AX is actually equal to B. So this is actually equal to V transpose minus U transpose B, because AX equals to B, since X is a feasible solution of the primal. Does that make sense? So now we have all these inequalities, but then if we rearranging, what do we get? We get that C transpose W plus U transpose minus V transpose B is greater or equal to 0. But if you notice, this is exactly what we wanted to prove. right? Which is this inequality here. Does that make sense? So this proves the strong duality, okay? So this proves strong duality. Does that make sense? So we just used Farkas lemma, which again follows as a consequence of the fundamental theorem of linear inequalities, okay? Okay, great. So now another consequence of LP duality, okay, is the following lemma, which is known as a fine Farkas lemma, okay? So if we have a system AX less than or equal to B, and if the system, let's say that the system has at least one solution, and suppose that we actually have an inequality, C transpose X less than or equal to delta, okay? So suppose that this inequality holds whenever X satisfies AX less than or equal to B, okay? Then, okay, here's what a fine Farkas lemma says, that there exists some delta prime less than or equal to delta, such that the inequality C transpose X less than or equal to delta prime is a non-negative linear combination of the inequalities of AX less than or equal to B. Does that make sense? So what the affine Farkas lemma is saying is that if I have a system of linear inequalities that implies another inequality, then this inequality is a relaxed version of a tight inequality that follows from the first inequalities to begin with, right? So, okay, so it follows in a very formal way. Okay, so this is a really remarkable consequence of LP duality. Okay. All right. Now, as a practice problem, okay, that we can discuss over office hours as well, if you'd like, use LP duality in Farkas lemma to prove the affine Farkas lemma. Okay. Okay. So, and now to conclude the lecture today, I wanted to talk about complementary slackness, right? Which is also another important theoretical tool. So suppose now that, okay, we prove strong duality. So suppose that the primal and the dual are feasible. So then we know that strong duality holds, right? And then we know that and we also know that the prime and dual are finite, right? So, okay. So if you take X and Y, which are feasible solutions, here's like three equivalent facts, right? So X and Y are optimal solutions to the prime and dual. The other one is C transpose X is equal to Y transpose B. And remember, this is the content of the strong duality, right? So 2 here is the content of strong duality. And the third one says that if xi is positive, okay, so if in the solution xi is positive, implies that the corresponding inequality, like y transpose times ai less than or equal to ci, is an equality, okay? So 3, what is 3 saying? For every xi positive implies that the corresponding inequality, like y transpose ai less than or equal to ci, okay, is an equality. So it implies this, right, like equals to ci. Okay, then, okay, so 3, so then, well, 3 is equivalent, okay, so 3 equivalent to saying that x, y are both optimal. Okay. So, and this is what this equivalence is what is known as complementary slackness, right? Like, so 2 is strong duality and 3 is the complementary slackness. And how do we prove this? Well, the proof is quite simple, right? So 1 and 2 are equivalent by strong duality, which is what we proved. And the content of complementary slackness is just that the 2 and 3 are equivalent. But how do we know that this is equivalent? Well, it's quite simple. Let's just write let's just write C transpose X minus Y transpose B. Now, remember, right? So X and Y, they're feasible solutions. So in particular, X is feasible. Therefore, AX is equal to B. So if I replace B by AX, I have that this is equal to C transpose X minus Y transpose AX. But now if I factor out X, what do I have? This is equal to C transpose minus Y transpose A. But now I can just write C transpose minus Y transpose A as the sum over the coordinates. But now what is the sum of coordinates? It's going to be the sum of all the n coordinates. And then I have the nth inequality here and xi. But now notice that xi, so we know that xi is greater or equal to 0, right? Because it's a feasible solution. But condition 3 implies that this sum, I equals to 1 up to n, xi ci minus y transpose ai, is equal to 0, which implies that C transpose X minus Y transpose B is equal to 0. Well, it's equivalent, right? Because if Xi is bigger than 0, then condition 3 is telling me that if this is bigger than 0, then this must be equal to 0, right? So when I sum, I get exactly 0. Does that make sense? So this is what complementary slackness is. Okay, and we're going to see an application of this in the next lecture. All right. So, okay, just to conclude, right? So what did we learn today? Well, we learned a little bit about mathematical programming. It's very general and pervasive in algorithmic life, so it's definitely something you should know. Well, it turns out that general mathematical programming is really, really hard, okay? And if you want to know how hard it is, I encourage you to think about it, okay? So it's harder than NP hard, but it includes NP hard, of course, right? And you know, but even special cases of mathematical programming, okay, have very striking applications. And today we saw linear programming and we saw the duality theory. We're going to see some applications of that in the next lecture, right? So, and so we're going to see some applications of combinatorial optimization, okay? And a lot of it happened here in University of Waterloo, so you should be proud. And there's also applications game theory and learning theory that we're going to see in the next lecture. Okay, so, okay. And this lecture is largely based on the book by Schreiber, okay, which is the theory of linear and integer programming. Okay, it's based on chapter 7. So if you want to look at it, that's the reference. That's the reference in linear programming. And since I only have 4 minutes, what I'm going to do is maybe I will talk about the fundamental theorem. If any of you would like to learn, I'll talk about it over office hours. Okay. So, and if I talk about it, I'll record and put it online. Okay. So any questions about the content of this lecture?
In the proof of the duality, you use Farkas lemma, but you don't